this object in peacock's tail that looks like an eye is called ocellus. Let's look at some mathematical graphs in here. This is a cardioid. Then it is surrounded by ellipse, and ellipse is surrounded by limacons, and plural of ocellus is ocelli.
Okay, so I have these polar equations written up here for you. R equals 1 plus sine theta is a cardioid, and then here I have an ellipse written in a little messy manner. Okay, yeah, I'll let you write a smarter equation. And here we have a limason, and then we got another limason. Okay, and sketching will be fairly easy if we are using a nice package to do that. So let us start our graphing. Remember, this is your equation of the cardioid. We go to the compute option, click on it, and then we will go down to plot 2D. Okay, and in the plot 2D option we want to select the option for making a polar graph. Okay, and click on polar, and the graph should show up. Okay, so we see the graph. Now we want to modify it, so click on this lower right corner, and we want to make the boundaries thick. Didn't see any axes or numbers in the peacock's feather, so we'll say, even though they are our guiding lines, we'll say don't show them. So here is our cardioid. Okay, now let's go ahead and add the other curves that we had seen by bringing their equations in. So what we shall do is this: click here, go to items plotted. You want to add items in here. Okay, so let's add our ellipse. Then we would like to add who? Our limason, the inner one. So here we can do this to add it in. Then we got 4.2 plus 1.2 sine theta for the outer limacon, and just click on this command button and we are set to see the whole thing. So we have these graphs, and well, you can stretch it in several different ways. This is one way. I see these curves coming, quite like we saw them in the peacock's feather, and we can go ahead and paint it in the manner we had seen it there. Like say here, we can give this the dark blue color. And what was it? And then here we can put light blue, and I think here we had this color, or we can make a peacock feather of any color we would like. I'll leave that fun for you to have. Okay,
now let us see how does a peacock show all these ornaments in the feathers.
धारा कृता धरन धरत पाग परत नहीं परन झन झन के झन नन 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 नादर दिन तनु नन नन तन तन नदीन तन नदर तानु ता नदर नदीन तन नदर ता नून नदर नदीन तन नदर ता
So what this show of hearts is going on for, not to show trigonometry or to show a golden spiral. The dance is going on to attract peahen, and it seems to work. That is, when the peacocks dance, it seems to attract peahen, and what has been seen is this, that if a peacock has higher number of ocelli in its feathers, then more peahen are attracted towards it. I don't know if the peahen count, but that's what the data shows. Okay, so we will go ahead, leave the peacocks and peahen alone, and let them do their own thing, and we will do mathematics. Our data comes from this paper by Manning and Hartley, in which they develop a numerical measure for these two variables, symmetry and ornamentation, and then show that the two are correlated. But before we see the calculations, let's just take a survey of symmetry as a measure or as an indication of beauty in various objects like this sculpture or this famous man-made architecture, or in this pair of cobra spectacles, or in this drawing that I made inspired by NBC logo. So Manning and Hartley in their calculations made a vertical line through the middle of the peacock train, ignored the number of ocelli on the line, counted the number on one side of the line, call it M, on the other side, call that number N, and then define the absolute value of the difference as train symmetry.
Here is this beautiful peacock that Gautam has made, and we can see Bhola is standing in the center, right here, showing us the axis of symmetry, and he likes symmetry. You can see the bell curve on his shirt. And here is Gautam. Gautam, how many ocelli on your side?
31.
Thank you, thank you. And Daya Shankar, how many ocelli on your side?
43.
And so what is the tail symmetry?
31.
Actually 43, and then you will subtract what was Gautam's? 31. That is the tail symmetry for this peacock is how much? 12.
Manning and Hartley, what they did was they recorded this data while doing what I was not able to do, that is taking pictures of 18 peacocks while they were facing the camera. And you can see here that as the number of ocelli increases, the train symmetry appeared to decrease. Now the peacocks were showing us a very good dance, so why don't we go ahead and look at this by using a display, say scatter plot, with number of ocelli as explanatory variable plotted on the x-axis and the train symmetry as the response plotted on the y-axis. So to do that, we'll go to this feature, what Excel calls chart wizard. Click on that. We'll choose a scatter. Go to next. You can see our plot is coming up. We'll go ahead and write the relevant things, like this is peacock's, peacock's tail. Okay, and here we have number of ocelli, and here we have the train symmetry. Okay, and we can finish it. We can remove some certain things that we may not necessarily want. Okay, enlarge the picture. Alright, here we go, and here we go, and our numbers in the x-axis are way out of bounds, so we will click on the x-axis and ask and change the scale not to make the things fit too tight. So let's start at 100, and here we go. we see a negative association a lot more clearly than going through numbers. Now, in order to see a mathematical relationship between the two variables, that is an equation that will help us guide through the pattern, let's click on this, and you can see this chart option coming up on the top on the toolbar. If you don't have this picture clicked, that option won't show up. Okay, so click on the picture, then click on the chart option, and we go to add trend line. Okay, now this shows a positive association, but is going to adjust according to our numbers, and let's have this thing do everything that it would do for us. Doesn't cost us anything. So here we go. You can see that we have a line with negative slope that will help us find the predicted value of train symmetry for any given number of ocelli within this range. Okay, and notice this value of r square, which is coefficient of determination. What does that help us understand? You can see that y values change from point to point as x changes. So there is variation in the y values with the variation in the x values. Okay, but if we walk along this line, since we know the equation, we understand that variation according to the values of x very well. So what this does is that this value of r square, that it gives us the proportion of the variation in the y values that is explained by this line that fits the data the best, or which is called the line of best fit. Okay, now before I close, first of all, notice this, that Peahen seemed to understand this line pretty well. Let's remove this anomalous thing here, that is -5 on the y-axis, because we defined the train symmetry as absolute values, and they can't be negative. So here we go. Okay, now we'll leave the other things like a distribution of the lengths, the lengths of the tails of peacock and other things in the upcoming attractions. Okay, now go ahead and work on your other regression exercises, and if you have any questions, let me know. Okay, thanks.